So one question which a lot of students ask me is, if the early atmosphere had so much CO2 and now we've only got a tiny amount, where has it all gone? And why are we so worried about global warming and carbon dioxide emissions if we've only got a tiny amount now compared to what we used to have? Well, they are both valid questions. So let's have a look at the composition of the Earth's atmosphere today. So we've got nitrogen is the main component of our air at around about 78%. So 78% of the air around you is actually nitrogen gas. Oxygen comes next, and that makes up around about 21% of the Earth's atmosphere. And that's already 99% of the total atmosphere. 78 plus 21 is 99. So, what is everything else? Well, we've got CO2, and we've got argon, and then we've got others. So we've got other gases as well, okay? CO2 is around about 0.04% of our atmosphere. Argon is around about 0.9% of our atmosphere. So we've got more argon than we do CO2. I put CO2 above argon because it's one which is more important to us. And so CO2 really is not present in that higher level in the atmosphere. However, it is very important because it is a greenhouse gas. This means that it will contribute to what we know, of course, as global warming. Even though it's only 0.04% of the atmosphere of the entire Earth is massive. I can't even put it into words how big it is. And that means that even 0.04% of that is a lot of CO2. And if, without us contributing to global warming, there would only be, let's say, 0.03% or 0.035%, the fact that we are contributing more and more means that global warming is happening faster. It would happen anyway, but the fact that we are contributing more means that it's going to happen faster, which is of course not good. Now, the first question I asked is, where has all this CO2 gone? And one way we can compare is that the early atmosphere is often likened to the current atmosphere of Mars and Venus. Mars and Venus, their atmospheres are thought to look pretty similar to what ours looked like a long time ago. Mars and Venus both have more than 95% of their atmosphere as carbon dioxide. And so the difference there is absolutely huge. Between 95% and 0.04%, that is a massive difference. So where has all the CO2 gone? Well, the main answer here is it's gone into living material or organic material. Organic material and living things. And well, you'll ask, how did it get there? The main process is via photosynthesis. Photosynthesis is a process in which plants and other organisms such as algae and bacteria can take in carbon dioxide directly and turn it from carbon dioxide gas into normally glucose. And that is going from an inorganic gas to an organic compound, glucose, which can then be used by organisms. This carbon can obviously end up becoming a protein in the plant. It could stay in the plant as sugar in terms of starch, and then the plants can be eaten by other organisms, obviously including us and other animals. That means that we can then use that carbon and we can use it to make our proteins, including our muscles and everything else, enzymes. It can be incorporated into our bones, into our teeth, and just about any one of our cells. And so that is a process in which carbon dioxide gas has now been trapped inside a living organism. And eventually, obviously, every organism is going to die at some point. And when this happens, a lot of the carbon, rather than being given us as CO2, some of it will be, but not all of it, a lot of the carbon will be trapped inside the organism, and many organisms can pile up at the bottom of oceans and things like that. So if fish die and everything else, they can end up at the bottom of the ocean, and then they form layers on top of each other. These form rocks known as sedimentary rocks. Sedimentary rocks. One of these sedimentary rocks, which you'll be very familiar with by now, is limestone. So e.g. limestone. And if you remember what limestone contains, it contains calcium carbonate. Okay, calcium carbonate. As you can see, we have carbon in there. Those rocks are then buried because more and more sediment will pile up on top of it. They are buried and they enter the rock cycle. What can happen from there is either they can form other types of rocks, they can be broken down into fossil fuels. Fossil fuels are, as I say, they are actually carbon containing fuels, and a lot of it has come from dead plant material, dead animal material, and those are different things in which can store carbon. That carbon, until we burn it, is actually trapped in those different forms. So in the rocks, in the fuels. If the fuels aren't burnt, then the carbon is not released back into the atmosphere as carbon dioxide. And so that is why when we are burning loads of fuels which wouldn't normally be burnt, we are releasing more CO2 into the atmosphere as would happen naturally. And one last thing, CO2 can actually dissolve in the oceans. So CO2 will dissolve. It can actually form something known as carbonic acid. You don't need to worry about that at the moment. But CO2 will dissolve in the oceans, and this can go on to react, form carbonates, and help form the carbonates found in rocks, such as calcium carbonate and limestone. And so remember, this is a really lengthy process. All of these processes take a long time, and that means that the early atmosphere took a long time to sort of create an equilibrium where the percentages of gases in the atmosphere weren't really changing. That equilibrium, or the equilibrium which coincides with today, was reached around about 200 million years ago. So around about 200 million years ago, we had about the same percentages of gases in the atmosphere as we do now. Now remember, from the early atmosphere we had two gases which were very common, which we don't find very often now. And they are methane and ammonia. Ammonia and methane. So what happened to these guys? Well, they would react with oxygen. Both of them would react with oxygen, and they would form different products. So we'd form carbon dioxide from methane, because obviously we've got the carbon from the methane there, and water. And we'd have to balance this. Obviously we need two of these, only one carbon on each side. And now we balance the oxygens, because we've got 4 and only 2 here. So that makes 4, that's balanced. And ammonia plus oxygen is going to give us nitrogen gas, and obviously water as well. And so balancing these, the number of hydrogens have to equal each other. So we're going to have 3 of these and 2 ammonias. Now the nitrogens equal to each other as well. And now the oxygens, we have 1.5, so 3/2 here. And the one thing here you really want to look out for is your nitrogen. Nitrogen is an extremely unreactive gas, and that means as this reaction was occurring, nitrogen would just build up and build up and build up. Whereas carbon dioxide from here obviously is going to be taken in via photosynthesis, and therefore it's going to go through many other different processes, whereas nitrogen is going to stay in the atmosphere as it is. That's why today we've got 78% of all the air contains nitrogen, or is nitrogen, sorry. 78% of the air is nitrogen. And so if you're doing the foundation paper, then do feel free to stop here. Finally, if you're doing the higher paper, we're going to have a look at how we separate the gases that are contained in air. So the fractional distillation of air involves separating various different substances from each other. This happens due to the different gases having different boiling points. But of course, the way we exploit that is we need to get them down to a liquid in order to boil them off separately. This will require us to cool them down to a very low temperature, which is going to be less than -200 degrees Celsius. So this is what I'm going to start off with, -200 degrees Celsius. And the main components of air really are oxygen, nitrogen, water, or water vapour in this case, carbon dioxide, and argon. There will be other components of the air. For example, methane is found in the air. Other noble gases as well, such as neon and xenon, they're all found in the air, but these are the main ones really. So we are going to reduce the temperature to around negative 200 degrees Celsius. Very important though is, first of all, we are going to remove, so the water and the CO2, well, they freeze at a much higher temperature than the rest of them. So if we are reducing the temperature, these will turn not only into a liquid, but they'll turn into a solid. So they will form solids when we get down this low, and that is going to block up the pipes in which we are carrying out this process. That's known as the liquefaction column. And so in order to counteract any sort of blockages and problems that may cause, we separate, or we remove, H2O and CO2 from the mixture. And that is in the form of ice and in the form of dry ice, because dry ice is just solid CO2. Okay, so moving on. Let's say that we had a column in which we had, this is not going to be the best drawing, you should be used to this by now. Let's say we had a column and we had these exit channels, so one here, and one down here. These are going to be at different temperatures to each other, so I'm going to put those in a different colour. Let's say that this is at around about negative 190 degrees C. This one is at around about negative 186, negative 186 degrees C. This one is at negative 183 degrees Celsius. Now you don't need to remember these temperatures, by the way, you just need to know the process. Sorry about that there. You just need to know the process. Now, if this is negative 200 degrees Celsius, this is our mixture coming in. This is going to contain, let's do this so you can see it. This is going to contain nitrogen, it's going to contain oxygen, it's going to contain argon. So our liquid coming in is nitrogen, oxygen and argon. Now again, you don't have to remember this, but just to give you an idea, if we've got nitrogen, oxygen and argon gas, nitrogen gas has a boiling point of around about negative 196 degrees Celsius. That means at any temperature above this, it is going to be a gas. Any temperature below this, so further towards negative 200 degrees, it's going to be a liquid. Oxygen has a boiling point of negative 183, and argon has a boiling point of negative 186 degrees Celsius. So let's take a look at our top funnel here. What's going to happen is at negative 190 degrees Celsius, that is cold enough for oxygen and argon to still be liquids, because you have to go above this, so further towards 180, negative 186, negative 183, you need to go upwards for those guys to become a gas. However, nitrogen will turn into a gas at negative 196 degrees Celsius, so even further down than this. So that means at negative 190 degrees Celsius, nitrogen has already become a gas. So nitrogen gas has already become a gas, and it's going to bubble out of here. So nitrogen here will leave as a gas. So we're going to have nitrogen as a gas. Okay, now we move down. At negative 186, that is cold enough that oxygen has not yet boiled. It's still a liquid and it's still in the mixture. However, argon at negative 186 is going to boil and it's going to become a gas. So that means that argon gas is going to exit here. So argon as a gas there. Finally, at negative 183, or really let's make it properly clear and we'll say negative 184 degrees Celsius down here, oxygen still has not become a gas. It's still slightly too cold in order for oxygen to boil, because negative 184 is below negative 183. So that means that oxygen here can leave as a liquid. So O2, liquid. The reason it can do that is because we've actually separated everything else from the oxygen. So here we have nitrogen given off as a gas and we collect it here. We have argon given off as a gas, we collect it here. And then we have oxygen. We don't need to boil that anymore, so we have that given off here as a liquid. These temperatures are just a guideline. They're pretty accurate. They're pretty much ballpark figures though, and you don't need to remember them. You do need to remember how we separate the components of air and the actual theory behind it, but you don't actually have to remember the specific temperatures. Okay, so I hope that's cleared up how we separate the gases. In terms of fractional distillation, if you don't remember fractional distillation as a process, and this has been a little bit alien, then please do have a look at my previous video on the separation of crude oil, where I go over that process in more detail. But otherwise, I will see you in the next video.